So today we're going to be going over 7b, which is linear and nonlinear relationships with tables and graphs. Our content objective is students will be able to determine if a table and graph is linear or nonlinear. Our language objective is students will be able to explain why a table or graph can be described as linear or nonlinear. Why am I learning this? Well, it's important for graphing linear equations. So first things first, we're going to go over some background knowledge. We went over how to find a slope based off of a table. What we did was figure out what the change in y over the change in x. So in this case, how did 4 become 10? You add 6. How did 1 become 3? You add 2. So you would check your ratios as you go to make sure they are the same so that you can prove that there's a constant rate of change. If you can prove that, then you can figure out what the slope is, which in this case is 3. So now let's take a look at something like this. So the instructions are going to be slightly different. It says determine if the following table represents a linear or nonlinear relationship. If it is linear, determine the equation. So what you're going to want to do first is, just like in the previous slide, we're going to find out the change in y over the change in x. So here, how did 4 become 10? You added 6. How did 1 become 3? You add 2. So the ratio would be 6 over 2, which is 3. Continue, how did 10 become negative 5? It got smaller, and you subtracted 15 to get there. How did 3 become negative 2? It also got smaller, and you subtracted 5 to get that. So now I'm going to stop. I'm going to check my ratio. And I'm going to say, okay, look, the negatives cancel each other out, so it is positive 3. So one thing I really want to stress is, notice as I check the change in y and then change in x, I check my ratio. Okay, and then I repeat. I do the change in y over the change in x, check my ratio. A lot of my students have the habit of just doing these little swoop marks, figuring out what the numbers are. They repeat all on both sides, and then they check their ratios last. You're going to find in this particular lesson, if you choose to do that, you might be wasting your time. Okay, so I highly suggest you do not do that. And I will point it out in the lesson when that does occur where you would be wasting your time. So going back, how did negative 5 become 2? It technically got larger. So here you are adding 3, negative 2 to negative 1, you are adding 1. Check your ratio. Positive 3 over 1 is 3, so things look good so far. Keep checking. Negative 2 to 1, you're adding 3. Negative 1 to 0, you're adding 1. Stop. Check your ratio. It does equal 3. 1 to 7, you're adding 6. 0 to 2, you're adding 6. So again, stop. Check your ratio. So here, we can say there's a constant rate of change. It is linear. And because it's linear, there is going to be an equation. Okay, in order to write down the equation, let's just recall the format of slope-intercept form would be y, let's try it again. Y equals mx plus b. I need to know what m is, and I need to know what b is. M, it's right here, all repeated about 5 times. M is 3. Okay, well, what about b? Just a friendly reminder, b is your y coordinate in the y-intercept. So here I'm going to say this is my y-intercept. How do I know this is the y-intercept? Because the y-intercept is when x equals 0. So since x equals 0, b would be 1. So now that I know what m is, okay, m is 3 and b is 1, my equation is going to follow this format. So it would be y equals 3x plus 1, like so. So now, what you need to remember and to understand is, since the ratios of the change in y over the change in x, essentially in this case we would refer to as slope, since they're all equivalent, this is a linear relationship. If these were not all equivalent, then it wouldn't be called a slope, okay, because slope represents a constant rate of change. So key thing to remember, okay, if all the ratios are equivalent, then it is a linear relationship. And so in this case, to answer the question completely, we had to determine the equation, and here it is. Okay, so that concludes our first example. So let's just take a look at the next one. So now it says to graph the equation. We've done this before. What do you do first? Well, you need to start with the with B, Since b is 1, well, let's write that lower. Since b is 1, I know that the y-intercept is 0, 1. So that's my starting point, 0, 1. My slope is 3, but I like to write slope as a fraction. So I'm going to go ahead and write that 3 over 1. So we're going to go up 3 over 1, up 3 over 1, up 3 over 1. But you know that I like for you to continue until you're completely off the graph. So in this case, starting at our starting point once more, we're going to go the opposite direction. So down 3 to left 1, down 3 to left 1, down 3 to left 1. Once you have all of these, simply draw your line through the points and make sure you have your arrowheads to show that they're going on forever. So notice for this particular problem, it did form a straight line. Since this graph is a straight line, it is a linear relationship. So notice in the word linear, the word line is in it. Okay, so for a linear relationship, you should expect a straight line. Okay, so based off of this graph, you can see that this is definitely a linear relationship. Why? Because it's a straight line. Okay, so moving on. So now back to number 2. This is similar to the very first example we just did. It says determine if the following table represents a linear or nonlinear relationship. If it is linear, determine the equation. So here, now I'm giving you the slope formula, which is the second y minus the first y divided by the second x minus the first x. So this essentially is the same thing as change in y over the change in x. So keep that in mind. Whichever formula works best for you, you can totally use that. So I'm sorry, not formula, definition. This one is your formula. Change in y over change in x is technically a definition. So here, you can think of it as, hey, how did a negative 4 become a negative 6? I know, you subtract 2, okay? How does 0 become 4? You add 4. So here you're going to stop and you're going to check your ratio. So here the ratio is negative 2 over positive 4, which becomes negative 1/2. Now I'm going to repeat the process. How does negative 6 become negative 5? Technically it did get bigger, so I'm going to put plus 1. And how did 4 become 2? You are subtracting 2. Stop, check your ratio. Notice they're still equivalent, so I'm going to keep going. How did negative 5 become negative 1? You're going to add 4 since it did get larger. How did 2 become negative 6? Well, you're subtracting a total of 8. You're going to take a second, check your ratios. They're still good. Next one, how did negative 1 become negative 7? You are subtracting 6. How did negative 6 become 10? Well, you're technically adding 16. So again, you're going to take a pause. You're going to check your ratios. Negative 6 over 16 is going to become negative 3/8. That is not equivalent to negative 1/2. So do I need to go further than that? No, because if you go ahead and do it, you're going to realize, okay, so this is the same, but it doesn't matter. This is not a constant rate of change in comparison to everything else. So guess what? Since the ratios of the change in y and change in x are not equivalent, okay, since they are not equivalent, this is not a linear relationship. In fact, I don't want you to say not a linear relationship. I want you to use the words non-linear. Okay, so let's write that somewhere here. We're going to refer this as a non-linear relationship. Why, you might ask? Well, because the ratios are not equivalent. Okay, so let's go ahead and move on to the next example. So now it says graph the points on the table. So here I'm going to go ahead and plot 0, negative 4, which is 0, negative 4, which is right here. 4, negative 6, which is here. 2, negative 5, which is here. Negative 6, negative 1, which is here. 10, negative 7, which is right here. And then negative 2, negative 3. So here, if we connect the lines, you'll notice the graph is not a straight line, therefore it is a non-linear relationship. okay? Because if it was a straight line, we would say it's a linear relationship. So here, notice if you are graphing it, it's different than when you are checking a table, okay? When you graph it, you need to see, okay, if it's a straight line, it's linear. If it's not a straight line, it's nonlinear. But in the example, let me just go back real quick. In the example of the table, we had to explain it is nonlinear because the ratios are not equivalent. Or you could have said it is linear because all the ratios are equivalent. So the explanations for tables and for graphs are slightly different. So I want you to keep that in mind when you're answering these questions. Okay, so on to another table. It says, determine if the following table represents a linear or nonlinear relationship. If it's linear, determine the equation. So again, we're going to use two different definitions. You use whatever you're comfortable with. You can definitely use a slope formula to find the change, or you can just simply do change in y over the change in x. So here, how did -3 become 3? You are adding 6. How do you get from 0 to 2? You're adding 2. So you're going to take a pause. You're going to check your ratio. It's 3. Okay, so moving on. How does 3 become 0? You are subtracting 3. How does 2 become 1? You are subtracting 1. Again, you have to take a pause, check your ratios, still looking good. So again, just a reminder, you can cancel out those negatives. Say negatives cancel out negative, making it positive. So moving back, how does 0 become 9? You're adding 9. How does 1 become 4? You're adding 3. Take a pause, check your ratio. So far, so good. Now the next one, 9 to 12, you are, let's see, you're adding 3. And from 4 to 3, be careful. You're subtracting 1. So here you're going to check the ratio. And you're going to say, oh, this one's a -3. So this one's tricky. If you didn't catch the negative, you might have blindly said, oh yeah, it's linear because the ratios are equivalent. However, not all of these are the same. This one is different. This is a -3 and the others were +3. So is there a constant rate of change? The answer is no. So since the ratios are not equivalent, okay, so since they're not equivalent, I would say it's not a linear relationship. But again, I would rather you use the words that it's a non-linear relationship. And if you were asked to explain why, you would say because the ratios were not equivalent. Okay? Moving on. So now, same instructions for number 4. You're asked, is it linear or is it nonlinear? If it's linear, determine the equation. So you have your two definitions. Sorry, not two definitions. You have your formula, or you can use your definition. So let's take it from there. How does -2 become -6? You subtract 4. How does -5 become 11? You are adding 16. So, sorry. Whew. I mean, you're adding 6. And so now you're going to check your ratios, and you're going to get -2/3. You're going to go again, -6 to -4, you're adding 2. 11 to 8, you are subtracting 3. So you're going to check your ratios. 2 over -3 is going to be -2/3. So far, so good. Now we're going to check -4 to -1. You are adding 3. From 8 to -6, you are subtracting 14. We're going to take a pause, check our ratios, and this ratio is unlike the other. So technically, we can decide right now that it is nonlinear. Why? Because the ratios are not equivalent. In fact, even if I show you this one, this would be further proof, okay, that it's not going to be a linear function. Okay, in fact, it is nonlinear. Why? Because the ratios are not equivalent. Okay, so since the ratios are not equivalent, I would say this is a nonlinear relationship. So be prepared to defend why to your partner of why it's nonlinear or why it is linear. So a quick reminder, it would be linear if all the ratios were equivalent. Okay, so the instructions are exactly the same. Now it's going to be your turn to try it on your own. So go ahead and quickly pause the video and see how well you do with this example. Okay, so now let's check our answers. Here, you're supposed to check all the ratios. In this case, we would have -2/4, which is -1/2. You're going to check the next one. You're going to get, make sure you check your ratio. You're going to get -1/2. So far, so good. Keep moving on. You get +4, -8, reduce. You still get -1/2. Still going strong. Keep going. -1 to -8, you're subtracting 7. -6 to 8, you are adding 14. Check your ratios, and they are all the same. So guess what? For this one is linear. Why? Because all the ratios are equivalent. And because it's linear, they're asking us what the equation is. So m is -1/2. We determined that. We need to figure out what b is. So in this case, I'm going to say my y-intercept is 0, -4, because again, y-intercept, you're looking for when x is 0. So since this is your y-intercept, I would say b is -4. Now that I know what m is, what b is, I can create my equation, which would be y equals -1/2 x minus 4, like so. So be prepared though, if your ratios are equivalent based off of the table, it will be linear, okay? So if you got that right, good job. Because that one was tricky because most of the examples we tried were nonlinear. So now let's talk about a linear equation. Basically, a linear equation is an equation whose graph is a straight line when you look at a graph. Okay, how can you tell from the table? You can tell off a table if all the ratios are equivalent. What about a nonlinear equation? Well, a nonlinear equation would be a graph that is not a straight line. So again, taking a look at a table, it's when all the ratios are not equivalent to each other. So the examples that we've seen previous to this slide. So right now, we're going to take a quick glance and see which graphs are linear and which are nonlinear. So here I would say the first one's definitely linear because it's a straight line. The next one is not exactly straight, so I would call this nonlinear. This one is a straight line, so that's linear, and this one is not a straight line, therefore it's nonlinear. Now I'm going to give you 4 more images. What I want you to do is go ahead and pause the video and tell me whether you think it's linear or if it's nonlinear. So go ahead and pause it. Okay, so let's see how well you did. First one, is it linear? Whoops. The answer, this is kind of tricky. It's actually nonlinear. It's not a straight line. Okay, so there's parts of it that are straight, but this I would not call a straight line. So here, is this linear or nonlinear? It is nonlinear. How about the third one? It is also nonlinear. And last but not least, it looks almost like this, except it's the opposite. So this one definitely is nonlinear as well. So hopefully you got all of those right. Okay, so how to graph a nonlinear equation? Well, first things first, you're going to need at least 5 ordered pairs. So basically an input and an output. If you're curious what input and output means, input is generally your x term and output is generally your y term. What do you put in for x is what you're going to get out for y. Okay? Then what you're going to do is where the input is negative, and you need to make sure, that you have an input that is negative as well as positive. You want both. So the best numbers I can think of would be -2, -1, 0, 1, and 2. Why these numbers in particular? Well, because they're the smallest numbers you can possibly use, okay, that it's requiring you to do 5 ordered pairs. So that's the smallest numbers. And you're going to learn pretty quickly with graphing some of these nonlinear equations. It grows pretty quickly. So again, the smaller the numbers, the better for you. So all you need to do after that is you're going to plot your 5 ordered pairs and then connect them. So let's take a look at what that might look like. So here, your graph is y equals x squared. So first, what I want you to do is look at that and say, okay, is that linear? Is it in the form of y equals kx? Okay, that's one way to check. I would say no. Okay, so if you can't already graph it using slope or intercept form, what you're going to want to do is create a table. So I'm going to go ahead, create an X and Y table. And remember from the previous slide, your input, which is what we're going to call X, you're going to want to choose the smallest numbers possible. You need some positives and some negatives. So I'm going to choose -2, -1, 0, 1, and 2. So here, -2, what is -2 squared? Well, let's see. Y equals -2 squared. What does that mean? Just a friendly reminder. This means -2 times -2, so the answer is 4. Repeat this. What about -1? Whoops. Let's reveal our ordered pair. So notice our ordered pair is -2, 4 because ordered pairs are written as x, y. So the next number is -1. What is -1 squared? So remember, I'm going to show my work here. Y equals -1 squared. This whole base of -1 is repeated twice. So -1 squared would be 1. So my ordered pair was -1, 1. Next one, 0. What is 0 squared? 0 times 0 is 0. So my ordered pair is 0, 0. Hey, this one goes to the origin. Next one, what about 1? What is 1 squared? 1 squared is 1. So my ordered pair is 1, 1. Last but not least, my fifth ordered pair, if I put 2 as my input, 2 squared is 4, so my ordered pair would be 2, 4. Now that I have my 5 ordered pairs, I'm going to go ahead and simply plot them onto my graph. So you're going to notice a general shape when something is, by the way, we call this a degree, when an exponent is raised to the second power. So degree is referring to the number of the exponent. So in this case, it's squared. So you're going to notice graphs that have x squared will generally have this shape, which we call a parabola. It's spelled P-A-R-A, parabola. But we don't read it that way. We read it as a parabola. Okay? So now, just looking at this, if you were to tell me, is it linear or nonlinear? I hope you would tell me that it's nonlinear. Why? Because it's not a straight line. Kind of looks like a hybrid of a U and a V. Okay, so moving on. What about if you were asked to graph y equals x cubed? So in this case, the degree is 3 because it's being raised to the third power. So taking a look at that, I'm going to ask myself first, does that look linear? Is it in the form of y equals kx? Nope. So because it's not in slope intercept form that I can easily recognize and start graphing right away, I'm going to have to create a table. So I'm going to use an x and y table. I'm going to choose the values for my input, which is referred to as x, as -1, -2, -1, 0, 1, and 2. So -2 is first. So here I have y equals -2 cubed. What does this mean? It means -2 times -2 times -2. Which would leave me with a -8. So here, my ordered pair would be -2, -8. Now, next number I'm going to try is -1. If you repeat this process, you will get -1. So that's my ordered pair. And then I'll try 0. 0 cubed is 0, so it goes through 0, 0. And then 1. What is 1 cubed? 1 times 1 times 1 is just 1. That's my ordered pair. Last but not least, 2. 2 cubed is 2 times 2 times 2, which is just 8, so that's my ordered pair. So notice I'm going to go ahead and now plot these 5 ordered pairs that I've developed. So this one looks different. This one is going to look like that. So this is definitely not the parabola that we saw in the last one. For this one, we refer to this shape as a cubic. Why, you might ask? Because it's raised to the third power, which can also be read as x cubed. Okay? So, again, if I were to ask you, is this linear or is this nonlinear? I hope you would say that it's nonlinear. Why? Because looking at the graph, it's not a straight line. Okay? Okay, so moving on. What about this? This one's slightly different, okay? This says x equals the square root of x. So I'm not sure if you remember square root, but with the square root symbol, it's going to be enclosed with these bars here. Square root means the distance from 0. So if you think about a number line, okay, for example, first, let's ask ourselves this. Is it linear? Okay, is it in the form of y equals kx? Can I tell what the slope is? Can I tell what b is? The answer is no, because of that absolute sign. So this is when I'm going to have to create a table. And again, you need at least 5 points, and we like to use negative 2, comma, negative 1, 0, 1, and 2. So here you'll see that I'm using negative 3 and 3. You don't have to, but I just want you to see the general shape of it all. So here, negative 3, if you were to look at a number line, okay, so here is 0, here's negative 3. How far is negative 3 from 0? You would say it's 3 away. So I'm going to say that's the square root of negative 3 is 3. So my ordered pair is negative 3, comma 3. There's my ordered pair. What about negative 2? Negative 2 is right here. How far is negative 2 from 0? 1, 2. So I would say the square root of negative 2 is 2. Same thing, negative 1 was the square root of negative 1. Well, it's 1 away from 0, so my answer is 1. So my ordered pair would be negative 1, comma 1. Plot that point there. So notice it doesn't matter if the number is negative. You're just trying to see how far it is from 0. And despite what you may think, there's no such thing as negative distance. If I were to walk backwards from here all the way to the mall, for example, I'm not going negative distance, it's still a positive distance. It doesn't matter if you're walking forwards or backwards, it's still distance, and distance is always positive. Okay, so here, what if you go nowhere? What is the distance? It's 0. Okay, what about 1? So here, let me show you. 1 is here. How far is 1 from 0? It's 1 away. So the answer is 1. So here, what's 1, 1? Plot that point there. Okay, what's the absolute value of 2? 2 is here. How far is 2 from 0? 1, 2. So it's 2 away. So the absolute value is 2. Same thing here. What's the absolute value of 3? It's 3. Plot that point. So here, you're going to notice the absolute value symbol has a specific shape as well. It looks like a V. Okay, in fact, I would actually prefer that you extend your lines a little bit longer in this case. Okay, and there you have it. Okay, so we're going to go over one more thing before we end today's lesson. I want you to take a close look. Okay, so here we have y equals x squared. Okay, and then over here we have y equals negative x squared plus 1. So notice, okay, I told you in the past we read graphs from left to right. If I were to read this graph from left to right, I notice it's going up, which is why that's positive. Now if you look at this looks almost identical to this, except it's upside down. I wonder why. Well, if I were to read this graph, it is going down, which is why it's a negative coefficient here. Notice this one touches the origin, this one does not. It was moved up 1. So this again represents that y-intercept. It's moving, it's not starting at the origin, it's starting at 0, 1. Here, what do you notice? Well, it looks like the same shape. It's the same parabola, but the main difference is it's a little bit more narrow in comparison to this one that's a little bit more wider. Why, you might ask? Well, it's because of this 2 here. The 2 is making it grow a lot quicker, which is why it's more narrow. And here, notice it doesn't start at the origin like in the first one. It starts at -5. So again, this is your, represents your y-intercept. It's not starting at 0, 0. It's starting at 0, -5. Now, one last one. Notice in this one, it is a lot wider, meaning it's taking a little bit longer to grow, which is why it's a lot wider here. And notice it is opening downwards because it is negative. And again, Here it doesn't start at the origin, it starts at 0, 6 because of this here represents your y-intercept. So a few more looks here. Same idea. Here, x cubed, notice it's going up as we read it. Okay, this one is going to be a little bit more narrow, okay, because it's growing faster. And notice it's not starting at the origin, it's starting at -1 as your y-intercept. Same here. This one's negative, so you'll notice if you read it, it goes downwards. Instead of starting at the origin, the y-intercept starts at 0, -9. Last but not least, in this case, this one is going to be a little bit more wider because of your small coefficient. And it is going down because it's negative. And once more, it's not starting at the origin, it's starting at 0, 4, because this number here represents your y-intercept. So this is kind of a preview of what you're going to see tomorrow. Okay, just the main thing I want you to see from this is when we read the graphs, we can see that it's positive. We can see that it's negative. Also, we want to check to see, look, the y-intercept at 0, -9. The y-intercept is at 0, 4. The y-intercept is 0, -1. So that is going to conclude our lesson for today. Thank you so much for tuning in. And like always, until next time, thank you. Bye.